For 50 years, Moore's Law was built on this one inescapable rule.
Right, you had to keep the chips small.
Exactly. Because, I mean, silicon manufacturing is incredibly messy at the microscopic level.
Yeah, if you try to bake a single semiconductor the size of a dinner plate, statistical probability guarantees it will have defects.
And under the traditional rules, a single defect just ruins the whole hardware, right?
Yeah.
You essentially have to throw the entire, billion-dollar silicon wafer straight in the trash.
Which is why wafer-scale computing was always considered physically and, frankly, economically impossible.
Until today, basically.
Yeah, until today. It is a fundamental shift in how the entire industry approaches the limits of physics. We are looking at a complete inversion of a 50-year standard.
Welcome to the Time and Market Deep Dive. Just to set the ground rules before we get into the actual mechanics of this, today's discussion is strictly for entertainment purposes.
Right, always important to note.
Yeah, we are going to examine market valuations, hardware architecture, secondary market data, all of that. But you should always seek professional advice for your own financial decisions.
Absolutely crucial to keep that distinction clear, especially on a day with, this much massive market movement.
Because today is Thursday, May 14th, 2026. And Cerebras Systems, which is trading under the ticker CBRS, has officially become a public company.
It is a huge day.
It really is.
Yeah.
And the mission of this deep dive is to sort of look past that opening bell hype, right? Past the standard media coverage.
Yeah, we really want to dig into the reality of it.
Exactly. So we are bringing together a whole stack of diverse sources today. We are pulling private market valuation data from PM Insights. We have deeply technical architecture breakdowns from the hardware engineers. And we are also looking at real-world case studies from places like the Argonne National Lab.
Which is where the rubber really meets the road with this tech.
So, okay, let's unpack this. I want to start by looking at the sheer financial footprint Cerebras established before they even rang the bell this morning.
Yeah, the financial momentum here really requires some careful analysis. Because according to the data from PM Insights, Cerebras generated just under $510 million in revenue in 2025.
Wow, okay.
Yeah, 509.99 million to be exact. And that represents a 75.71% year-over-year growth rate.
That is aggressive scaling.
Very aggressive. They have been scaling their operations massively, and the private secondary markets were reacting to that trajectory well before this public offering.
Right.
Over the last 90 days leading up to this IPO, shares in the private secondary market surged by roughly 99.1%.
Wait, I need to stop and just analyze the math on this for a second because it's kind of wild.
Go for it.
So back in their Series H funding round, which was, a couple of years ago, they were valued at $23 billion.
Correct.
And the IPO today targets a valuation between $34.7 billion and $35 billion. They're looking to raise about $3.4 billion in capital.
Right, which is a massive jump.
It is. And if we run that $35 billion valuation against roughly $510 million in revenue, that is, let me think, of 44.25 times trailing revenue multiple.
Yeah, it's a staggering number.
That is an astronomical premium for a hardware company. I mean, even at the absolute peak of the AI infrastructure boom, Nvidia was trading at a fraction of that multiple.
Oh, absolutely.
The market is pricing in absolute perfection here. To justify that kind of premium, Cerebras can't just be making like a slightly faster processor.
No, they have to be doing something physically different, something that completely breaks the traditional cost curve of the semiconductor industry.
Exactly. So what exactly are they doing differently from Nvidia to justify that kind of multiple?
Well, what's fascinating here is that they're doing exactly that. They are completely rewriting the physical rules of manufacturing to bypass what the industry calls the yield problem.
Okay, the yield problem.
Right. To understand how institutional investors are justifying a 44 times multiple, we really have to examine why the industry believed larger chips inevitably meant worse financial yields, and how Cerebras just solved that 50-year-old paradox.
Let's explore the physical realities of that then. Because they build a processor called the Wafer Scale Engine, right?
Yeah.
Currently the WSE3.
Yes, the WSE3.
And to really grasp the scale of this thing, we have to compare it to the current industry standard.
Which would be something like Nvidia's H100 GPU.
Exactly. A traditional high-end AI chip like the H100 is manufactured on a 300-millimeter circular silicon wafer.
Right, and standard practice is to cut that wafer up into dozens of individual pieces.
Right, you can fit about 72 H100-sized chips on a single wafer, But Cerebras, they don't use a diamond saw to cut the wafer at all.
No, they don't slice it up.
They utilize the entire 300 mm surface as one continuous, unbroken piece of silicon.
Which is just wild when you think about it. It results in a single processor that is 57 times larger than the largest GPU currently on the market.
57 times.
Yeah. It houses 4 trillion transistors and 900,000 AI cores on one contiguous surface.
That is just mind-boggling.
It is. But that scale is exactly where the traditional manufacturing laws start to break down. Because manufacturing silicon at TSMC's 5-nanometer node, which is the facility and process Cerebras uses, is highly advanced, but it is never flawless.
Right. Physics just gets in the way.
Exactly. The physics of photolithography guarantee microscopic imperfections. At that 5-nanometer scale, there is roughly 0.001 defects per square millimeter of silicon.
Okay, let's run the statistical probability on that. If a company is making traditional small GPUs and they encounter, say, 50 random defects scattered across a large wafer, a few of those individual chips are just going to be ruined.
Right, you just toss the bad ones.
And Nvidia and AMD account for this. They even build redundant cores into their small GPUs, so if a defect hits one specific subcore, they laser it off, disable it, and sell the chip anyway.
Exactly. It's a known cost of doing business.
But the Cerebras WSE3 is over 46,000 square millimeters.
Right.
So statistically speaking, every single wafer they produce will be struck by roughly 46 physical manufacturing defects.
Without fail.
So if they operate by the old rules where a hardware flaw ruins the contiguous device, their manufacturing yield would basically be zero.
Yes, they would literally never produce a saleable product.
Which is crazy to think about.
And that is the exact mathematical wall that stopped companies from even attempting wafer-scale designs in the past. But Cerebras bypassed this through a combination of microscopic core design and software-defined routing.
Okay, walk me through that.
So before laying out the broader architecture, they engineered incredibly small, fault-tolerant AI logic units. Each individual core on the WSE3 is merely 0.05 square millimeters.
Wow, that's tiny.
It is. To put that in perspective, that is roughly 1% the size of a processing core on a traditional H100 GPU.
Okay, I see. Which means the blast radius of a manufacturing defect is tightly contained.
Exactly.
If a flaw hits an H100, it might compromise a significant percentage of the processing real estate. But on the Cerebras wafer, a defect only destroys a microscopic 0.05 square millimeter unit.
Right, it's just a tiny pinprick.
But wait, containing the blast radius isn't enough, is it? I mean, you still have a giant continuous chip with 46 dead zones scattered randomly across it.
True.
The software compiler has to somehow navigate a flawed piece of physical hardware and make it operate perfectly. How does it do that?
So the mechanism they use to solve this operates right at the compilation level. Cerebras includes a small percentage of extra redundant cores built directly into the wafer itself.
Oh, clever.
Yeah. When the system boots up for the very first time, the hardware runs a complete diagnostic sweep across all 900,000 cores. It specifically identifies the 46 or so physical defects on that unique wafer.
Here's where it gets really interesting then, because I picture this like a massive city grid combined with a modern GPS system.
That's a great way to look at it.
Right. If you build a sprawling metropolis, but you know in advance that 46 random intersections are permanently blocked by like unfixable potholes, traditional hardware routing would just crash as soon as data tried to cross those intersections.
It would just halt entirely.
But the Cerebras compiler draws a custom map at boot up. It treats the dead cores like permanent road closures.
Yep.
The software just routes the data down an alleyway to the spare cores they built in, so the entire city keeps functioning perfectly. The data traffic ignores the physical potholes entirely.
And that routing logic allows them to achieve something the industry previously thought was impossible. Because the software dynamically maps around the hardware flaws, Cerebras achieves an astonishing 93% silicon utilization.
That's incredible.
It really is. They are effectively utilizing more of their raw silicon than companies manufacturing small traditional GPUs. They've completely eliminated the historical yield penalty associated with large chips.
Okay, so they successfully engineered their way out of the yield paradox.
They did.
But a clever manufacturing trick doesn't secure a $35 billion valuation unless the resulting hardware actually performs, right?
Oh, absolutely. Performance is everything.
So we have to look at how this monolith stacks up against the undisputed heavyweight of the sector, Nvidia's Blackwell B200 architecture.
The performance metrics are really where the structural advantages of wafer-scale computing become apparent. We can look at independent third-party benchmarks from SemiAnalysis, comparing the Cerebras CS3 system directly against Nvidia's B200.
And what do the numbers say?
When tasked with running Meta's Llama 370 billion parameter model for inference, the Cerebras CS3 processes data 21 times faster than the B200.
Wait, 21 times faster, not 21%.
Nope, 21 times.
That is a generational anomaly. I mean, usually a new hardware release offers, what, a 20 or 30% performance bump?
Yeah, historically, that's what you'd expect.
Achieving a 21x multiplier, while, I'm reading the same benchmarks here, costing 32% less and utilizing 1/3 less power than the Blackwell GPU? That just breaks the traditional scaling laws of the industry.
It really throws the old metrics out the window, and we see similar throughput disparities on other models, too.
Oh, really?
Yeah, running OpenAI's open-source 120 billion parameter model, the Cerebras system generates over 2,700 tokens per second.
And Nvidia's B200.
NVIDIA's D200 outputs roughly 900 tokens per second.
Wow. Okay, so the obvious question is how? How are they moving data fast enough to keep 900,000 cores fed without stalling out?
It all comes down to the von Neumann bottleneck, specifically a concept known as the memory wall.
Right, the memory wall.
In modern large language models, the limiting factor isn't usually the compute cores themselves. It is how quickly you can actually move the massive model weights from the memory modules into those processing cores.
Because traditional GPUs utilize high bandwidth memory, or HBM, right?
Exactly. It is highly advanced memory, but it still requires ferrying data off the main compute die across a physical connection substrate into a completely separate memory chip, and then back again.
Which is incredibly energy intensive and slow. I mean, GPUs were originally designed to render graphics, processing massive blocks of parallel data all at once.
Right, they were made for gaming, essentially.
But generative AI models don't operate that way during inference. They generate outputs sequentially, just one token at a time.
One word after another.
So every time an NVIDIA chip needs to generate a single word, it has to fetch the entire massive model weight across that tiny wire.
Yep.
It's like, imagine having a brilliant mathematician who has to commute across a bridge to read a single line in a dictionary, commute back to their desk to write down one word, and then cross the bridge again for the next word.
That is a perfect analogy. And that data movement latency is the primary bottleneck in AI inference today. Cerebras handles this through an architecture they call weight streaming.
Weight streaming, okay.
Because their processor is the size of a 300-millimeter wafer, they actually have the physical real estate to bake a massive amount of memory directly onto the silicon.
Oh, wow.
Specifically, 40 gigabytes of ultra-fast SRAM sitting immediately adjacent to the logic cores.
So they basically removed the bridge entirely.
Wow.
Dictionary is just sitting right there on the mathematician's desk.
The weights of the neural network stream continuously from a centralized memory unit directly onto the giant wafer.
Yes.
And because the memory and compute are on the exact same piece of silicon, the internal bandwidth is just orders of magnitude higher than a traditional GPU cluster. And if we connect this architectural difference to the broader trajectory of the industry, we can really see why this specific latency advantage is so critical right now.
How so?
Well, we are moving away from simple text-predicting chatbots. The industry is pivoting heavily toward complex reasoning models and agentic AI.
Right, models that actually think.
Exactly. These systems require low latency, batch size 1 inference. They need to analyze a problem, test multiple logical pathways, and reason through a chain of thought before ever providing an answer to the user.
That takes a lot of quick iteration.
It does. If a traditional GPU cluster takes 30 minutes to execute a complex agentic task because of that memory wall latency, that severely limits enterprise adoption. Nobody wants to wait half an hour.
Yeah, that makes sense.
The high memory bandwidth and pure processing speed of the wafer-scale engine shrinks that iteration time dramatically.
I do want to inject some skepticism here, though, because hardware performance doesn't just exist in a vacuum.
Fair point.
I mean, Nvidia didn't become a multi-trillion-dollar entity solely on raw silicon performance. The benchmarks for Cerebras are impressive, but Nvidia maintains a massive moat that Cerebras has to cross.
Yes, they do.
And that moat is built entirely of software.
The CUDA ecosystem. It is undoubtedly the most significant hurdle for any AI hardware competitor.
Right.
The entire modern machine learning software stack was essentially built on top of Nvidia's proprietary CUD platform. Developers have spent over a decade optimizing their code specifically for Nvidia hardware.
It's hard to break that habit.
It really is. The depth of ecosystem integrations, the diagnostic tools, and just general developer familiarity heavily favors Nvidia.
So how is Cerebras dealing with that?
They are addressing this by designing their compiler to interface directly with standard frameworks like PyTorch and TensorFlow. Theoretically, this allows developers to run models without writing any custom code.
Right, just plug and play.
But as you know, breaking developer habits and migrating enterprise pipelines away from the industry standard is notoriously difficult.
Which means we really need to evaluate how this technology actually performs in the messy real world, outside of these perfectly controlled benchmarking environments.
Absolutely.
We need to look at organizations that are currently utilizing Cerebras systems to handle complex, large-scale problems.
And the deployment scale we are seeing provides a very clear picture of institutional confidence. Consider their partnership with the global technology group G42.
Oh, right down in Texas.
Yes. They are currently constructing Condor Galaxy 3 in Dallas, Texas. This facility is an 8 exaflop AI supercomputer built by linking 64 Cerebras CS3 systems together.
Okay, wait, let's define that for a second. An exaflop represents 1 quintillion floating point operations per second.
It is a massive amount of math.
You have an 8 exaflop facility dedicated purely to AI workloads, provides an immense amount of localized compute power.
And G42 has already utilized the previous iterations of the Condor Galaxy network to train significant foundational models. They trained JACE-30B, which stands as the leading bilingual Arabic language model.
That's huge.
And they also trained MED42, a specialized clinical medical model that actually surpassed Google's MedPolem in accuracy evaluations.
Wow. Okay. And the deployment at the Argonne National Lab offers an even deeper look at the actual scientific implications of this.
Yes, definitely.
Because they integrated the Cerebras architecture into their workflow, specifically to accelerate cancer research.
Right.
Their teams rely on massive deep learning models designed to predict how specific tumor cells will respond to varying drug compounds.
And under their legacy systems, researchers at Argonne had to distribute these massive data sets across large clusters of traditional GPUs. They noted that training these drug response models often required weeks of continuous computation.
Just wait around for weeks.
Exactly.
But when they transitioned those specific workloads to the Cerebras hardware, the training time was reduced from weeks down to mere hours.
Which is a complete game changer.
And the impact extends into foundational physics, too. Argonne utilized the system to analyze gravitational wave data, searching for the specific signatures of black hole collisions.
Right, looking at the cosmos.
With their traditional hardware, the analysis actually ran slower than real time. The sensors were generating data faster than the compute cluster could process it.
And operating slower than real time in physics research means valuable observational data is literally just being discarded.
You're losing information.
Exactly. But the high bandwidth architecture of the Cerebras system allowed the lab to run their classification models in real time, perfectly matching the data ingestion rate of the sensors.
So what does this all mean for researchers? I mean, when you reduce an experimental cycle from a month down to a few hours, it fundamentally alters the iteration cycle of science itself.
It absolutely does.
It democratizes curiosity. If an experiment takes a month and costs millions of dollars in compute time, researchers are inherently conservative. They only test the safest, most likely hypotheses.
Right, you don't take risks when it costs that much time and money.
But if that same workload executes in 2 days, scientists can test radical theories. They can tolerate a much higher failure rate.
There is actually a specific note in our sources from Nick Brown, the head of AI at AstraZeneca, summarizing this exact dynamic.
What do you say?
He stated that training workloads, which historically took over 2 weeks on a large cluster of GPUs, were accomplished in just over 2 days on a single Cerebras system.
That's incredible.
Yeah, allowing them to iterate more frequently and achieve accurate answers orders of magnitude faster. It completely changes what questions scientists are even willing to ask.
And the physical architecture also changes how these systems scale, right?
Yes, dramatically.
Because connecting thousands of traditional GPUs requires writing tens of thousands of lines of complex distributed systems code.
It's a nightmare for developers.
Developers have to manually slice their model into tiny fragments, just to fit into the limited memory of individual chips.
Yeah.
But Cerebras developed an interconnect fabric called SwarmX, right?
Right, SwarmX. It allows them to link up to 2,048 CS3 systems together. And because the memory is decentralized and the data streams continuously, the compiler treats the entire 2,000 system cluster as a single logical device. You don't have to rewrite everything.
So the memory capacity of a fully scaled SwarmX cluster maxes out at, what, 1,200 terabytes of external storage?
Yes, 1,200 terabytes.
Just to ground that number for a second,
Okay.
1,200 terabytes allows the system to natively hold a neural network with 24 trillion parameters.
It's almost hard to wrap your head around.
It is. For context, industry estimates place massive models like GPT-4 at roughly 1 to 2 trillion parameters.
Right.
So they are provisioning the hardware architecture to support the next several generations of scaling laws without requiring a rewrite of the distributed computing logic,
Which circles right back to the IPO multiple we analyzed earlier.
the 44 times multiple.
Exactly. The institutional investors purchasing shares at a $35 billion valuation are betting that the AI industry is transitioning from a compute-constrained environment to a memory bandwidth-constrained environment.
Oh, interesting.
Yeah, they are paying a premium for a structural solution to the latency bottleneck.
So synthesizing all of this source material,
Sure.
today marks the massive public debut of Cerebras systems under the ticker CBRS.
A historic day for the market.
Truly, we have examined how they tackled a physical limitation that stood for half a century, utilizing microscopic 0.05 square millimeter cores and compiler-level routing to achieve a 93% yield on a Wafer scale chip.
Beating the yield paradox.
Exactly. We've looked at the semi-analysis benchmarks showing a 21x inference speed advantage over Nvidia's B200 architecture by eliminating the von Neumann memory wall through SRAM weight streaming.
Right.
And we've tracked the real-world utility from reducing Argonne National Lab's cancer research cycles from weeks down to hours to powering 8 exaflop facilities for G42.
It really highlights a critical juncture in hardware engineering. The physical demands of software are forcing a total reevaluation of manufacturing standards.
So, why does this deep dive matter for you, the listener? Because the artificial intelligence tools you interact with daily are evolving rapidly. As they transition from simple text generators into autonomous agents capable of complex reasoning and long-term planning, the underlying physical hardware dictates the boundary of what is actually possible.
Yeah, the hardware sets the speed limit.
Right. Latency, memory bandwidth, and compute efficiency determine how fast, how affordable, and how intelligent those daily tools can become. Cerebras has positioned its wafer-scale architecture as the physical engine required for that next phase of human-machine interaction.
Which leaves us with a really compelling sort of strategic question to ponder as we watch the market digest this IPO today.
What's that?
For 50 years, the global semiconductor industry operated on the firm belief that manufacturing large chips was an economic impossibility. If Cerebras continues to validate that wafer-scale computing is highly viable and structurally superior for generative AI workloads, will the massive legacy foundries be forced to abandon their standard practices and pivot to wafer-scale designs?
That would be a massive shift.
It would. And if the industry does shift, how does an incumbent giant like Nvidia, whose entire global supply chain, packaging infrastructure, and data center footprint is perfectly optimized around small modular chips, pivot their entire business model to catch up?
That is the multi-billion-dollar question underlying today's valuation. The future of computational power might not belong to whoever can slice the silicon the thinnest. It might just belong to whoever figures out how to serve the whole wafer.